for inviting me to this symposium, and it's nice to share with you our experiences with this AFM setups that we're using. And of course, let's say I'm also here just to talk a bit more general about the science that we're doing. And so to introduce very basically, I'm from Bologna. I'm a physicist, and of course the work that I'm doing is happening, of course, in the context of a nice group where I'm collaborating with, and we are in the physics department, and we are experts in semiconducting materials. So we do a lot of different experiments, and one of these experiments is then also the nano-characterization experiments with the AFM that I'm going to describe you, but they're all embedded, let's say, in the context of applications and how these materials can be used and employed into novel devices. We are in Bologna, and 200 years, okay, it's an old university, but Bologna is the oldest university of Europe, so it's almost 1,000 years, and of course that's something that I've always have to emphasize. Another difference is, let's say here they dig into the earth and go down into the ground. These are the famous due torri of Bologna. So here in the Middle Ages they tried to climb in the air, of course, going high. And when you're on top of the towers, that's the view that you have on Bologna. And as you can see here, so it's something that I took from the Lonely Planet internet page. And this year Bologna does not even was also selected as a very nice tourist destination. So it's a #1 Lonely Planet destination to visit in Europe. So like to motivate you to come and visit us. And it's a beautiful view, and it's a nice place because it combines both. Let's say it has a vibrant, large university, but it has also culture. So don't only go to Rome and Venice. When you go to Italy, come also to Bologna, and we're very proud about that. There are a lot of ways also for students or researchers to come and visit us. We have an international master student course in English. That's our master program, Material Physics and Nanotechnology. We have PhD positions every year in physics, and there are also postdoc opportunities in our group if you're interested in material physics or material science in general. Just contact me. Okay, so to give you a broad introduction to what we are doing. So here I'm presenting you one of the devices that we are proud to have invented this year. And it demonstrates the concept about where you can get with radiation sensors. So radiation sensors, ionizing radiation sensors, of course, there's a big need to track ionizing radiation as they are a potential health hazard. And you would like to know, without big technical issues, to kind of have a monitoring about what's happening with such radiation. If you see modern radiation detectors, of course, they are like bulky instruments that require high tension in order to separate excitations. But this is something like where you can get when you employ modern semiconducting materials, and if you combine also different electronic worlds. This is a passive radiation detector, and it's wireless. So passive in the sense that it does not even need a battery. It contains just an integrated circuit from RFID. And the nice thing is, okay, silicon integrated chips, they are cheap. Such a chip is like in an RFID tag, so it costs 1 cent. But it has already a nice complexity. It can harvest the energy that it gets from the antenna by the radiation, elaborate it digitally, produce an ID, and then probe a little sensor. And the sensor is something that we build with different electronic materials. That's large area oxide electronics. So here's our radiation sensor array. So the power is enough to electronically probe, let's say, the status here of our sensor, and then transmit the information back in the RFID signal to the receiver. And all this device is something that basically you could build for a few seconds, yeah, and just disperse it around. You have an ID, and then just monitor radiation. So that's kind of the things that we envision in our group. Of course, there are a lot of severe material problems that you have to solve. And one of them, of course, is to transfer semiconducting materials to large areas and to flexible areas. And that's where I get into the details here. Another application that we're very interested in is applications that are related to bioelectronics. So how to interface electronic devices with our bioelectronic signals, right? So bioelectronic signals is, for example, your ECG signal. If you want to know if your heart is still beating, okay, there are simpler methods to know it, but that's something how you can monitor it and track it. And it's important to track it, for example, if you want to see, for example, if in a worker, if he gets health stress due to heart diseases, similar things, you can get to more complex signals like EMG, muscular signals, and also signals, of course, from nerve cells. And this is not just a simple electrode, what I'm presenting here, but it's a semiconducting material that interfaces directly with the skin and amplifies, so to say, these signals. And moreover, it's a polymeric material that is also built on a biodegradable substrate. So it's something that we think that could open up to new ways of interfacing electronics with our body. Again, also here you have the problem like to understand more than just the electronics, to understand additional materials properties that are relevant for such an interface. And I'm going to show you about that. Okay, one of the main concepts, of course, that we have to deal with when we pattern electronics on large flexible areas is strain. If you go to the very simple case of an elastic material, strain is then very easy to define. So you have an object, you stretch it, and then you can define easily the strain as the ratio of elongation and its original length. If you have tensile, you can stretch it, then it's tensile strain, or you can compress it. Of course, both create strain in your material. That's, of course, relevant for elastic electronics, like our skin is something that is elastic. If you just go to flexible electronics, then typically you have the problem that maybe you have a substrate, and on the substrate you have your active layer patterned, and the problem is then when you bend it, you create a surface stress. So either you bend a convex or convex shape, you get a compressive or tensile surface strain, and you can easily calculate the value of such a strain by the radio of curvature. Of course, there are also ways just to work around and avoid any kind of stress in an electronic device, and that is a very beautiful example that is shown here from Martin Kaltenbrunner. And the idea here is that you just have a single layer, a very single layer, very thin layer of electronics, and what you can do in order to avoid any kind of stress is just to pattern it exactly in the middle of your flexible foil. Then you can avoid any kind of surface stress. Of course, that requires that you just have a single layer of electronics and that it's very thin. When you start to have multi-layer electronics, or when you want to build a material that's sensitive to something that happens in the exterior, so you have to put it on the surface, then again, you have the surface stress problems. So which kind of materials can you imagine in order to produce large area flexible electronics? Basically, nowadays we have three major material classes that we can employ. One is amorphous silicon that you can deposit by physical methods. We have organic electronics. These are just small molecules or polymers that you can get in a solution. You pattern them on a surface and you have a semiconducting behavior. Or finally, we have oxide electronics. They are also deposited by physical deposition methods. They come in even amorphous structures, which can be nice and produce also nice semiconducting behaviors. For the works that I'm going to introduce you into how we investigate strain effects in electronics, I just chose the example on the organic electronics. Okay, now in order to give you a little introduction into these electronic effects, I guess that there are quite a few of you who don't work with microelectronics. Let me introduce you briefly transistor, okay? So that's the main component that you have in your mobile and any integrated circuit. So whenever you talk about microelectronics, the first device that you look at is a transistor. A thin-film transistor is shown here. So this device contains basically three electrical contacts, source, drain, and gate, and it contains a semiconducting layer here shown in orange. Now, a transistor is kind of an on-off switch, and what you can do is you apply to the gate a potential, and here it's a negative potential, so you have negative charges. Now you have here a dielectric, so this is kind of a capacitor, and you have then the counter charges on the opposite layer. So you produce kind of carriers, you accumulate positive carriers in your semiconducting channel, and now of course you know when you have kind of a channel that is populated with positive charges that are mobile, you can have a current that goes through this layer, right? On the other hand, if you would apply here a positive potential, you would deplete the semiconducting material from carriers, and then it wouldn't be possible to have any further current across this layer here, so the switch would be switched off. This is shown here in the characteristics. So you can see here the regime where it's switched on. You have current. It's a negative current, so it's a p-type transistor here. And you have here a regime where you are in the positive potential range where there is no current, so the switch is turned off. With organic electronics, you would deposit such a semiconducting layer using an ink. So basically you deposit small droplets, the solvent evaporates, the molecules deposit on the surface, they arrange into small nano or microcrystalline structures that are shown here. So in violet you have, let's say, the electrical contacts, and the gap where you have the semiconducting channel is here shown in yellow. This is now my first AFM image, just the morphology of such a single crystal to show you how it bridges the source and drain electrodes. Of course, that's a large structure that's kind of chosen by us in this large way in order to investigate effects easier. But you can see that how such a single semiconducting crystal nicely bridges source and drain electrodes below the surface. Of course, then you have the gate in order to populate the structure with carriers. Okay, how to do the tests of strain? Basically, we deposit these transistors on a flexible surface, and then we start to bend it, and then we can investigate just by contacting the transistor and measuring it, how it works. This is kind of how we investigate like the bending with a small camera, and then we can calculate the surface strain. You can see that here, of course, it's not comparable to something that is elastic. However, you get, if you bend it strong enough, you can get to strain values on the order of a few % in such electronic materials, so something that is definitely not negligible. And these are now the characteristics that show how such a transistor degrades. So it can resist initially to some bending up to roughly 1% of surface strain, and then it starts to degrade. You see that the degradation comes in abruptly, so you have here almost an order of magnitude change in transport properties, but then it is again at plateau, and important also, it still maintains, let's say, some transport qualities, and then it degrades further and further. And this is, let's say, an easy experiment that is easy to measure, but it's much more difficult to understand where is the defect here, why does it happen, and what do I have to improve in order to, let's say, have more stable electronics. And now the question comes, of course, how do I investigate it in more detail, this fracture mechanism? Right, so basically you are here at the point where you have to take a decision. You can say, okay, I'm just happy by watching and maybe see small fractures and then understand what's happening. So that would be the children that watches the television and watches an elephant, and now you can ask me, I myself have children, is watching enough to understand the animal, to understand the elephant? And I would say, no, as humans we have kind of this predisposition to use our eyes a lot to understand things, but in order to really understand what's happening in an animal or what is an animal, at the end you would have to touch it. And for this problem of electronics, it's exactly the same. Of course, people have used a lot of SEM techniques, so optical microscopy, in order to investigate fracture. But with photons, you cannot probe electronic properties. So the touching that is important here is to understand locally what happens to the electronics, where do I have barriers in transport. And the nice thing is that that's something that you can do with AFM. So with AFM, clearly you have the information about the structure, but you have also the local electrostatic interaction. And let's go into detail to see this here. So the basic experiment that you have in order to probe the electrostatics locally with an AFM and a transistor is what I've shown here. So again, it's a transistor. You have all three contacts, as I've described before, but now you have an additional fourth contact. That's your probe. That's metallic. So here's a gold-coated AFM tip. With the AFM, you can easily wire your transistor, as you see here. You can measure all the characteristics that you need. You can polarize it as you want, and at the same time, you can now approach with your AFM tip and do all kind of different experiments. Now, the question is, of course, which kind of electrostatic forces emerge in such an experiment, and there we have to switch way back in time in order to macroscopic systems and look at the so-called Kelvin-Probe Experiment. It's not so intuitive, but let me just give you a brief introduction. So the Kelvin-Probe Experiment, what you basically do, you have two different metals. Let's just suppose we have, for example, gold and aluminum, okay? And we bring them in close contact. And we measure the forces that build up between the two of them. So in the first case, basically, if we just have a an unconnected piece of metal, it's not a reproducible experiment. It would be one of the experiments where a student could easily lose a few months of work. Problem is, you have electrostatics. A metal without an electric contact could be easily charged, and then you have some effects that are not depend on humidity. You know, in Bologna, this is really an issue. So what you would have to do here is, first of all, establish an electrical connection. So, for example, you could just put the two metal blocks into a short circuit, and then you can see that you have an attractive force. And that's the so-called Kelvin force. And this force, it builds up when we go a little bit into, have a look at let's say, what actually are metals, and in particular, what is, let's say, the difference between a noble and a not so noble metal. And this is shown here in the energy diagram. It means that if you have a noble metal, you need a lot of energy in order to remove an electron from the metal. And that's here the so-called work function, which is large for gold. If you have a not so noble metal like aluminum, we all know this, you basically need very little energy to remove an electron from it. Now, if you put the two of them into contact, that's shown here, what happens is like, the electrons, they feel that in aluminum they are not so stable, they could be more stabilized in gold, so they flow across your cable and move into the gold. So what you have the buildup of a small negative charge here at the surface, and the counterbalancing charge. The whole system is neutral in the aluminum. You have two opposing charges, so they attract each other, right? And that's basically what happens in the Kelvin-Probe experiment. Still, it's not quantitative. You measure some force. The question is now, how can you become quantitative and really get a value that characterizes such a force? And the trick is then to apply a potential that exactly is large enough that the force is exactly zero. Kind of that nullifies this electrostatic force due to the differences in work function, and that is what you're doing here. And then you know exactly that the potential that you apply is equal to the differences in the work function between these two metals. Right? That's the macroscopic effect. The nice thing is that this effect you can exactly translate it to the AFM, to the nanoscale. Of course, then it's not so easy anymore to measure forces, because at the scales when we are almost in contact with the surface, we do not have only electrostatic forces, but we have van der Waals forces, we have a lot of different forces. And that's a problem when you do the electrostatic AFM experiment always. So you have to find a way how to separate precisely the electrostatic forces. Now, the nice thing is that thinking of frequency space and dynamic AFM, there is a very, very elegant way to do so. And the nice thing is that it's an electrostatic force. So a potential that I apply, it does not need to be a DC potential. I can also apply AC potential, so at a very specific frequency. And this specific frequency is something that then kind of targets my electrostatic forces, and I can look at them at the precise frequency space and kind of catch them out and just separate them from all the other forces. How it's done is shown basically here. That's what I've described before. You have just a capacitor. If you have a voltage difference, you have an energy of a capacitor and basically a force. You see that the force gets larger the difference in the surface voltage. Now, what you can apply here is if you apply an AC voltage, this delta V, then the force also gets this alternating part. And that's what I mean by separating the electrostatic forces. So let's just do something very practical, not going into detail of the equations. Just think about a normal non-contact AFM experiment, right? So we have our tip. We do not have electrostatic interactions. We are very close to a surface. Our tip oscillates, right? And we have our feedback system active. That here the oscillation amplitude is just constant and everything is working nicely. We measure our height and we are happy. Now we scan our surface and we get to an area where we have an electrostatic interaction. Let's say there are, for example, some charges trapped in the surface. There is a different metal. What happens is we get, due to this Kelvin effect, we get kind of a charging of our tip. We have this additional attractive electrostatic interaction. Okay, if we just think about our non-contact experiment, what this would lead to, a shift of our resonance curve, the amplitude would go down, the feedback system would activate and just pull our tip apart from the surface. So it would look like as if there is a step in surface height, right? An artifact due to electrostatic forces. The surface is flat. What can we do? Now what we can do if we think about the Kelvin experiment, if we would at that moment exactly apply a force that counterbalances this electrostatic interaction, we wouldn't have such a problem. We would just have to kind of know or separate the electrostatic forces. And now by looking or by applying an AC voltage at 17 kilohertz, for example, what happens is if there are electrostatic forces, we see that our tip, in addition to the high frequency oscillations of non-contact mode, we would see an additional oscillation at 17 kilohertz. And if we just track this oscillation, apply a DC voltage in order to remove it, then we exactly know that we are at the condition where there are no further charges present at our tip. So we again would approach the surface. There is no electrostatic interaction, and we wouldn't see the artifact in surface height. So the topography would be correct. In addition, we can map the DC potential that we apply to our tip in order to nullify these forces, and we would get an additional channel of data acquisition, which is just called surface potential, which would contain information about the electrostatics. Okay? And that's how scanning Kelvin-probe microscopy works. Of course, the technical implementation needs, in addition to the usual non-contact with a single lock-in amplifier, as it's amplified in the NX10, you would need a second lock-in amplifier in order to precisely separate the frequency at which your electrostatic oscillations occur. If you have these two lock-in amplifiers in your instrument, so that's the default for NX10, the nice thing is you can do just one scan and immediately acquire all two data channels without artifacts. Just the example from the transistor. This is the topography, the height. You can see even in the height that here you have the electrode, here you have your channel, and here you have your semiconducting crystal. So it goes from the electrode, it stretches into the channel. Now if you look at the KPFM, the surface voltage, you see that all three materials correspond to a different constant voltage, and that is because they're all characterized by different work functions. You can look at gold, so our metal contacts here are of gold, and the gate contact below is made of aluminum, and you can see that there is a potential difference that basically corresponds here to the difference in work functions between these two materials, and then you have here an additional value that corresponds to, let's say, the Fermi level of your semiconductor. All this is very important and relevant information for a lot of semiconductor device-related aspects. For example, differences in work function are a problem when you want to inject carriers from one material to another. So you have to think about them. So just this measurement contains a lot of information in order to improve devices and understand what's happening. However, this is kind of a thermodynamics thing. Work function is just thermodynamics. If we think about a transistor, we think about also transport, like how fast do carriers move, are there traps or are there barriers they have to overcome. So in a transistor, we go even a little bit further, and we do not look at the system all connected to ground, but we look to a system where a current is flowing across our microchannel, and that's, we can do the same experiment. Now, what we observe here, so that's the whole microcrystal bridging source and drain electrodes, and here is the KPFM map. So what you can see here is that, of course, our electrodes are no longer connected only to ground, but just the source electrode, that's at 0, and the drain electrode, you see it's biased externally at -5 volts. And what you can now see here with this color map is that, let's say you have this gradual decrease along your microcrystal towards your drain. And this is a potential, but from that information, you can get a lot of knowledge about how carriers move and how much carriers are present there. So here I've just plotted a cross-section, and if you say that, of course, you can say that, let's say, the current density or the overall current through the crystal remains constant. We are in a state of constant current flow. What you then can do, you can use the derivative of this information to calculate the electric field. You know also the gate voltage, so knowing the capacitance, you can also calculate local carrier concentration, and that's all the relevant parameters that you need in order to characterize a transistor. Okay, but anyway, that's a working transistor, so we want to break the transistor and then see what happens to this device in order to fully understand what's going wrong. This is the experiment, so you can stretch a device and do at the same time an AFM experiment. I wasn't so sure in the beginning of this experiment whether that's actually possible, but it is, so that's nice. And you get morphology images that are shown here, but they do not contain really information. I do not see a large opening of a crack, right? Because at the end I have a small percentage in strain. If there are some nano crack, okay, I would really go into detail and have to look everywhere in order to find it, which would take quite a long time. If I instead look at the KPFM map, things get interesting. So initially, I see of course, the voltages between source and drain, the crystals that bridge here, the two electrodes, and now I apply strain 1%. I see that, let's say, the electric field starts to increase here at the contacts, which means that charge injection gets more difficult at these contacts. I start to apply more and more surface strain, and I see the appearance of kind of abrupt changes in surface potential, which always means that locally I have a very, very strong electric field, and this electric field is then of course needed in order to push carriers over a barrier that kind of emerges. And at the end, if I go to the complete destroyed device, I see that I have a lot of these very, let's say, local barriers where a strong electric field is needed in order to overcome transport. Right, when I have this information, of course I can quantify it in more detail and just have a look at local transport properties. Here you see how these barriers emerge at the contact, and then in the channel you can calculate kind of a local sheet resistance for such a barrier, and you see that these barriers have transport properties that are orders of magnitude worse than just the pristine, intact semiconducting crystal. If we go now into, again, morphology mode and look just at the very, very close scale to what's happening at these barriers, we see that there is the emergence of these very small nano cracks in the crystal. Of course, there must be some physical origin of this defect. So it's happening that, in fact, this crystal cracks and creates this barrier, and indeed I can see that that's exactly where I have the buildup of the strong electric field. If I apply more strain, I can also see that these cracks, they kind of widen. Yeah, so the rest of the crystal remains just connected. It's just kind of the crack that widens and kind of absorbs the stress. So applying this combining this information from the microscale and the macroscopic behavior, now I understand that initially, of course, I have a nice channel. Once there is the appearance of cracks, I have barriers in transport, but it remains stable for some time because these cracks can absorb some kind of strain, and then I continue by breaking it. I have the appearance of additional cracks, and the mobility drops down until it's completely destroyed. What is important here is that at the surface, these cracks might be large. But of course here at the interface, that's where my charge transport happens. Here it's very relevant to think also that you have adhesion. So the adhesion of the microcrystal to the surface is something that kind of, we assume that it helps to stick these gaps together so that however I see at the surface it cracks, but however I still know that there is some possibility to carriers to overcome them. Okay, I can apply this technique now to different systems. For example, I can investigate more in detail how the morphology or how the deposition techniques that I apply in order to deposit my semiconducting ink on a surface impacts on its stability towards strain. So that's something that we've done with a group from Barcelona. They have this coating technique where they have a roll and they have this ink and then they deposit it, and by rolling into one direction they align crystals somehow and they see differences. So the question was, let's say with AFM, can we see differences in morphology? Of course you see a different direction of the crystals and different crystal sizes, so that's related to all the small structures that emerge on such a microelectronic device. And you can also then investigate with KPFM how this impacts on the transport from the contact into these microcrystals, where there is a significant impact depending on how the arrangement that you choose during your deposition. Another interesting application was from oxide electronics. So that's a device from a company where they had problems. That's the device that broke, and they started to optimize the semiconductor depositing techniques in order to, let's say, improve. So here again, this is like a microscopy image. You see source and drain, you see the gate, and the semiconducting material is just here in the channel. That's the oxide electronics. That's where the company expected the problems during strain, because this is a metal. So, and you can see here you do not have a gradual decrease in electronic transport. You have just, you can apply strain or a curvature up to 1.2 centimeters or something like that. If you go beyond, the device is completely broken. We started the KPFM experiment. The interesting part is we never saw any problems at the semiconductor, so we started to suspect that maybe it's the metal that creates the problem, and indeed, using the KPFM, it was easy to do like a large scan of the whole structure and see where the barrier is, and then we had a look into morphology, and we see that indeed that here it's the metal that creates the problem, and it's molybdenum, it's not gold, so molybdenum is a much more brittle metal, it's even more brittle than the semiconductor, so here the target for optimization of such devices, now they know that first of all they have to focus on the metallic contact if they want to improve the bending stability of the devices. So to conclude this first part, it's just basically two very basic conclusions to give you on the way. One is that the nice thing with AFM is, especially if you have an AFM where you have a lot of space below, you can combine it with all kinds of different kind of small equipment that you put below it. This is a device to stretch devices, bend them, and at the same time you can apply electrical contacts and measure things, and it's possible to do atomic force microscopy in these more complex arrangements, even without big difficulties. The other thing is, of course, by touching or getting in close contact, you get much more information. For us, semiconductor physics group, it's of course the electrical transport properties that is very nicely to obtain with these kind of experiment. Okay, second part of my talk is the bioelectronic interfaces. And here, of course, you have to think much more about questions that are related to biology, like how soft are materials, are they biocompatible, and what are cells feeling, or what is the biological system feeling when it's getting into contact with these electronics that we pattern on the surface and these devices that we build in order to acquire bioelectronic signals. Again, let me introduce the kind of materials that we investigate in this research. These are so-called semiconducting polymer composites. So the semiconducting polymer is actually this part here. You see it's a long polymer chain made of aromatic molecules just connected one to the other. And the nice properties of these molecules is that once you have a positive charge inside such a chain, due to the pi system that is delocalized along the whole chain, such a charge can be transported all along the polymer chain or also hop from one polymer chain to another. So it's a polymeric material that transports whole charges, similar to something that you know just from a traditional semiconductor device. Question in these devices is, how do you introduce these positive charges? Of course, you can apply field effect, but you can also use some kind of doping technique. And the doping comes here in the form of a polyanion. You see here that this is also a polymer which from time to time has these negative charges. And these negative charges, they counterbalance the mobile positive charges in your semiconducting polymer. The whole system is a kind of composite in the sense that you do not get a homogeneous mixture, but it's a material that has its own nanostructure. Now, for a semiconductor, it's of course relevant, as I've shown you in the transistor, to modulate the amount of charge carriers that are in your semiconductor in order to have a modulation of the current. And you can do this in a so-called electrochemical way, but by reducing or oxidizing your materials. So it means that when you go in the reduction direction, you add an electron that fills the whole charge. Of course, you have to stay electrostatically charge neutrality, so you introduce also an ion into the whole system, and this would be, let's say, the composite that is not conducting anymore. Okay, so you have these two states, a conducting and non-conducting state. Okay, this should be a video, but probably it's not so nicely working. Anyway, it's not very complicated. What you see here is basically one experiment where you can vary the doping. So basically you have a small Petri dish. You have the surface all covered with your semiconducting polymer composite. On top of that, you have a liquid, and then you have the electrochemical setup, which is like counter and reference electrode in order to control the potential that you apply in the liquid. Of course, you also need to contact somehow your semiconducting polymer composite. That's done with a working electrode. Now, when you apply oxidation and reduction, you can see that here, of course, conductivity changes, but also optically, you see a very nice difference. So this gets blue, and then it gets transparent. It gets blue transparent because the oxidized one here, it's transparent, and this one is nicely blue because you have, let's say, stages in the band gap that emerge that change your color. So you can also optically see nicely the doping state of your system. Relevant, let's say, the doping, it's always, of course, as you can see here, it's something that is not only related to the exchange of electrons, but also ions and also water. Of course, ions are always accompanied by a water shell, so they go in and out of the polymer. Okay, next question, why is this material system then relevant for bioelectronics? Okay, Well, there are two main reasons why this is a material that is actually something that is opening new opportunities to measure bioelectronic signals. One is that just imagine what you have to actually do in bioelectronics. Bioelectronics, our own electronics, our nerve signals, they are based on ions. It's electrical signals, but they are ions, right? So it's in a liquid, and you have just ions that move around, and by their moving around across a membrane, they define different potentials and very small current fluxes. And that's how our nerve system elaborates, let's say, all what I'm saying, and or even if you're sleeping, however it's active. Now, electronics is something different. You have electrons that move around, so it's from a material point of view, it's something that is completely different, okay? Electrochemists, they like it. It's what they investigate. Because, of course, when you have hydrogen evolving by applying a current, what you do is you put in electrons, they get ions, and at the same time they create hydrogen and oxygen, so you have electrochemistry. You can imagine that in a body, electrochemistry is something that you do not want to have, right? Because if you have hydrogen evolution at an electrode, it will destroy your cells. You can imagine what's happening. So electrochemistry is something that we do not want here. So we basically want to have a material that converts the electrons of our electronics into ions without employing electrochemistry. How is it happening? It's basically something where you need a capacitor with a very, very large capacitance. So something that is not just two-dimensional, like a typical Debye-Helmholtz model where you have a metal, right? The ions can only approach up to a certain extent to the metal, and then it's just limited by geometry. They cannot get closer, so the capacitance, the interaction is limited. If you have these semiconducting polymers, the nice thing is they are mobile for electrons, so the electronic charges kind of can enter it like into a sponge, and at the same time it's also mobile for ions. Also ions can enter. So you create this kind of three-dimensional space where ions and electrons can encounter, and thereby you create materials that have a very, very large capacitance. Or for electronics, you would speak of a very low impedance if you think of an AC signal that has to traverse this interface. So if you do the impedance spectroscopy, if you have just a normal electrode, you can see here that, of course, at lower frequencies, you get very high impedances, and it will be difficult to transmit signals across this interface. Now, if you apply such a composite, you can see that you can drop it even orders of magnitude, meaning that you facilitate a lot the transmittance of information, and of course, that's very, very important if you have small signals. That's one reason why such materials could be of interest. The second reason is they are biocompatible. So you can grow cells on them. They are not toxic. It's a semiconductor that remains active without being toxic and without degrading. If you put silicon in water, it oxidizes, you have an oxide layer, and it's done. These materials here, in direct vicinity of water, of course, they maintain their electronic conductivity, and they are not toxic to cells. Even more interesting, the way cells grow on these materials depends, for example, on the amount of charges that are inside. So that's one of the first questions that we wanted to address. For example, how is this happening? I mean, is it something that is related to the morphology of these materials, to whatever kind of strange effect? And it's clear. I mean, it's an electronic material. There are a lot of possible effects that can happen in such a system. You can think about mechanics. You can think about just surface morphology that changes with potential and so on. So let's say that was kind of the starting point where we started in our group to apply AFM in order to understand, for example, here in a precise way, what are the cells actually feeling when they are sitting on top of such an electronically active material. And now the nice thing is, of course, you can do AFM in liquid, so that's the setups that we use. Yeah. So here it's very schematic. You have here your cantilever, your tip, you have your small window in order to have a nice path for your laser beam to measure its vibrations. So that's a typical AFM in liquid setup. But then you have to think, of course, also that here you have an electronic material. So you have to have the electronic contact. Without electrochemistry, you have to seal these contacts with the external electronics, of course, nicely from the liquid that is inside here. And you need your typical electrochemical system in order to control potentials in liquid, which is the potentiostat. And of course, this one here, you have then to interface it with your AFM. Can be easily done with our setup, and it's working nicely. Here's some pictures of the measurement cells that we apply. So the first one is just a very large polymer film that you have here in the center, where you can just measure a macroscopic thin film, or you can also contact just micro electrodes and see what's happening at a smaller electrode scale. Okay, going to morphology at the end, this is not so interesting. In air it's nice because, let's say, with stepping mode, you can nicely observe these Nanocomposite morphology. When you go into liquid, it gets a bit more difficult to observe the nanophase separation in the material. However, what you see is that basically the morphology is not so different in function of, let's say, the doping level of your material. So the amount of charges, it does not really have an impact on your topography that you observe in liquid. Okay, so that's for sure not what the cells are feeling, what is kind of making a difference. We go further and we measure mechanical properties. First thing is that, of course, you have to realize it's clear when you have such a film and you dried it in air and it's just dry, it behaves very different than from when you put it into surface, because at the end, it's not a hydrogel, but it's, however, a material that swells, so it takes up water that can also nicely be observed in AFM. So this is just as measured in air. Here there was a scratch. When you put it in water, you see there is a kind of swelling of 63%. At the same time, you also see that the mechanical properties, they change when you do indentation experiments. So in air, you have 3 gigapascal. If you go to liquid, you get something that is much softer and is on the order of 20 megapascals. However, also here, oxidation state was not the one that was impacting on the mechanical properties. The interesting thing that you then can start to observe is just when you do the live experiment. While you're measuring AFM, you start to change the oxidation state and then see what's happening. And this is an image that I take where I have just a line scan without moving forward or backward in the slow scan direction, and just collecting in time always the same line while I vary the potential applied to my polymer. And then I can see these kind of images. You can see that here I have basically a variation in surface height. I do not have a variation in morphology, so these stripes here, they just remain there. It's just that their height kind of changes. This is the plot, so you see that these changes amount even to values of 100 nanometers. So it's kind of an actuating system controlled externally by the potential that I apply. Why is that happening at the end? I can also understand it. Not so difficult, because when you're in the oxidized system and the reduced system, the oxidized system, it does not contain ions, while the reduced system does. And the ions are, of course, they have a liquid shell, so it's clear that more volume enters into the reduced system, so it's where I observe the swelling, the increase in surface height. What is nice, of course, I can vary frequency space and then understand, for example, what limits these actuation properties, do kind of electroswelling impedance spectroscopy, which is nice, which is, for example, difficult to obtain if you just do a macroscopic optical measurement of such swelling properties. Now, going back shortly just to biology, what I was doing, so what was the system that I was investigating is, so that's a polymer composite, that's a cell, a lot of different interactions. The cell has to adhere to the surface, it has ionic channels, it has to do all kind of its biochemical actions. And now what we did in collaboration with another group, we did patch clamp experiments, and we did these on differently oxidized or reduced polymer composites. And what we observed is that, in fact, the electronic state of our polymer impacts strongly on the bioelectronics of the cell, in particular on the membrane potential. And now, thinking further of what actually is happening, imagining this material as a kind of ionic sponge, it's clear that, let's say you have a system where you can accumulate, for example, if you do the reduction in a solvent that contains potassium, you can accumulate potassium and you can release it. And the sponge effect, that release of ions, is something that we think that is locally acting here on the electrochemical potentials that build up at the membrane. And this release of ions, it's actually what's happening and what's impacting then on how cells behave on oxidized or reduced materials. Just to keep further in telling the story. Okay, regarding AFM, again, here's the conclusions. Touch your samples, takes the risk of also damaging them. I mean, you have to know actually what you're doing, like here with a tiger, and then you get much more knowledge about your materials and what is happening with respect to these bioelectronic interfaces. Of course, it's important to measure in liquid. All these systems, you do not ever have an idea what, if you kind of probe morphology or properties in dry, you have to go to the same conditions where the cells are doing their work. And that's also an electrochemical condition, so you need this electrochemical control. Nice thing in the swelling experiment is the high spatial resolution that you have for these actuation properties, and also a nice temporal resolution that you can obtain with AFM. And of course, combining this information on electronic and material properties with the morphologies, and that what kind of is important to understand in a very general way, these bioelectronic interfaces. Okay, with that, I'm at the end of my presentation. Let me just thank all the people who collaborated for achieving this work. So the group in Bologna with Beatrice Fraboni and a lot of other students and PhD students and postdocs. We collaborated with the university, also with the Department of Electrochemistry, with the University of Cagliari, who are experts in electronics, University of Barcelona, who did these different organic semiconducting coatings, and also with Lisbon regarding oxide electronics. And thank you for your attention.
Yeah, thank you, Mr. Cramer, for this nice talk, and definitely you needed the 4 minutes and to stay in time. The talk is now open for discussion, and please introduce yourself and raising your question.
So hi, my name is Victor Bergman from Park Systems Europe. Thank you for that very nice talk, and I have a question to the first part. So I assume you deform your substrate and then let it go back to equilibrium and measure it again. Are you also able to deform and measure it while it's deformed, or do some kind of experiment?
No, we measure actually while we deform it.
Why do you deform it?
It makes a big difference. So we do not measure it, let's say, in real time, because while you deform it, you have some larger movements, which would go beyond the response possibilities of the piezo actuator, of the AFM. So we lift a little bit, we move and get into a system where we have a larger surface strain, and then we measure the system while it's actually in a strained system. If we then would go back in order to relax everything and investigate again, the effect on the electronics would be different, because these cracks, they close, so the device can recover partially and would be different, yes.
Oh, okay, perfect, thank you.
Okay, do we have another question?
Yeah, maybe I should emphasize this. I mean, this, for me, I was not expecting it, because, you know, with AFM, you have this anti-vibration table. You always think you need something that is very stable and so on, but if you build a nice sample holder and you mount it nicely on your XY scanner, it's stable. We had no problems. I mean, of course, you cannot do indentation experiments, right? You work in non-contact, but then the forces are so low that even with much softer materials, I could stretch them and measure AFM. So, and that's amazing. So it's opening for us a lot of opportunities, and it's really interesting. Yeah.
Hi, Cristiano Bonetti from Bologna. So, sorry, my voice is too low. So I have a question about Kelvin-Probe. The frequency that you use as an alternate voltage applied to the tip you mentioned. Have you checked the spectrum of the cantilever, and you choose a frequency that is out of any vibration of the cantilever, or you choose a particular frequency for a specific vibration of the cantilever?
Mm-hmm. Yeah, that's of course a question that of course you have to answer. I mean, one thing, we do it like contemporaneously to the non-contact mode. So the resonance frequency is where you apply, let's say, the vibration, the frequencies that you observe in order just to map the morphology and all forces. So you want to stay, of course, distant from that in frequency space. Now you can go to higher frequencies or lower frequencies. So here with non-contact, you use, of course, a pretty stiff cantilever, so you're already at high frequencies. So what you would do here is you go to a rather low frequency, and in particular frequency where you do not have interference with other things. So basically where you can have the best signal-to-noise ratio possible. And 17 is something that I checked it, but indeed 17 seems to be the best value. Never really understood why it's precisely 17 and not 23. But
yeah, you have a reason. In fact, you can use what you want. But if you check, when I do the same in my microscope, when you check the spectrum of the cantilever without electrostatic force, so you can see that you have some peaks due to, I don't know, for example, it's very stiff. So you have a peak and the rest is flat. And the second point is, what is the voltage that you apply to the Kelvin-Probe to have enough contrast in Kelvin-Probe?
Mm-hmm. So that's the amplitude of the AC voltage, and that's typically 1 to 3 volts. For these systems here, where the signals are rather large, I mean, I'm talking about, let's say, variations from 0 to 5 volts. With 1 volt, you can have nice images.
Okay. Thanks, perfect.
Okay, so we like to stick to the schedule, but we are a forum, we are a network, so further question, please directly to the speaker. Thank you again, Mr. Cramer, for the presentation.